Hello, my name is Todd Tomashek. I'm an engineering manager at Intel in our machine learning performance team, and I'm the architect of the AI Analytics Toolkit. I'll be presenting an overview of the Python machine learning and AI offerings from Intel and how these can be used to unlock performance and scale. Thank you, panelists, for giving me your time. I've been with the Python project at Intel since its beginning about 6 years ago, and we've maintained our commitment to two key principles, performance and usability. And we have focused on enhancing the existing ecosystem tools rather than fragmenting it. Unlocking performance in Python requires working around the interpreter's global interpreter lock and implementing the key underlying algorithms in native code. To achieve this, we've been connecting the data scientist's favorite Python tools, such as NumPy and Scikit-learn and Pandas, to Intel's performance libraries, such as the Intel OneAPI Math Kernel Library and the Intel OneAPI Data Analytics Library. For example, we accelerate NumPy with our MKL FFT, MKL random, and MKL UMath packages, which accelerate FFTs, random number generation, and universal math functions, in some cases up to 400x. Implementations and native code allows concurrency at multiple levels that were previously unavailable. Further, Intel's been investing in accelerations across the data science pipeline rather than focusing on only one stage, such as model training. With data science reaching nearly every industry, end-to-end performance improvements are critical. And while these techniques are powerful, we don't want every Python developer to need to be an expert in C or C++. So we committed to usability by connecting them through well-known tools with only small code changes. And finally, the open, active, and talented Python community is really the driving force that is making Python the #1 language for data science. And Intel wants to empower the community's contributions. To help that, we've made our next generation OneAPI Data Parallel C++ compiler available on Anaconda's default repository. DP-C++ is based on open, not proprietary standards and allows programming across CPUs and GPUs. Open and performant, that's our commitment. Let's look at an overview of the AI and data science optimizations powered by OneAPI that Intel currently offers. As you can see, Intel offers a wide variety of optimizations and tools for AI developers and data scientists. These drop-in accelerations are offered for all steps of the data science pipeline, ranging from tools such as Modin, which distributes Pandas data frames by changing a few lines of code, to XGBoost and TensorFlow for increased training and inference accelerations out of the box, to Scikit-learn, which increases Scikit-learn models, inference, and analytics tools with a few lines of code added. We won't be getting into the details of everything listed on this page, but as you can see, Intel has optimized and created a lot of ways to improve AI developer and data scientist workloads. Underneath, these optimizations are powered by OneAPI libraries such as OneDAL, OneDNN, OneCCL, and OneMKL. But users don't need to interact with these packages directly in order to see scale and performance gains. These offerings are available on Anaconda, or can be downloaded together as a bundle through the Intel OneAPI AI Analytics Toolkit. Let's look at a couple of the tools that accelerate common steps in the data science pipeline. Pandas is the favorite Python tool for organizing data throughout the data pipeline, and our solution for accelerating Pandas is the Intel distribution of Modin. Modin and OmniSci are open source projects targeting data frame processing, and Intel engineers have been working closely with those projects to add significant optimizations. At a very high level, the performance gains are achieved by partitioning the data along optimal axes, allowing concurrent processing of the data frames during key operations. Our distribution brings these projects together in a simple installation, and with only a few lines of code you see here, you can gain up to 38x improvement on ETL operations with large New York taxi datasets. Not only are these results accessible by changing only a few lines of code, but they allow the process to use the full system memory and the I/O capabilities, allowing this to scale to tens of millions more records than is possible in competitor products. You can get the Intel distribution of Modin by installing the Intel AI Kit package using Conda and either the Anaconda defaults channel or Conda Forge, shown here, or you can install the Modin All package. Then you import Modin as PD and use Pandas as normal. For more details, please visit Anaconda's blog post referenced here or the Intel distribution Modin product page. Similarly, Scikit-learn is the favorite tool for Python machine learning, and Intel's extension for Scikit-learn brings near-native performance to the Python developer by connecting the high-level Scikit-learn operations to native implementations in the Intel OneAPI data analytics library. Simply install the Scikit-learn IntelliX package along with Scikit-learn itself and execute the patch operation you see below to unlock the performance. Patching can be easily turned on or off for A/B testing or experiments. And after patching, simply import and use sklearn as usual, but you'll see significant performance improvements. Scikit-learn IntelliX is available in the Intel OneAPI AI Analytics Toolkit, from the Anaconda Defaults channel, from Conda Forge, and on the Python Package Index and PyPI. We actually performed a demo where we recorded data science workflow experimentation using these tools. I won't be able to go through that demo or show it here, but it's available online at the link in this presentation. And there's a link at the end of this presentation too, so you can look at it later. Intel is committed to open standards, and the Intel OneAPI Data Parallel C++ compiler, based on open standards programming model, is now available for free in our OneAPI-based toolkit. To support Python developers, the Data Parallel C++ compiler is also available on the Anaconda Cloud, and using it is as simple as installing DPCPP, or as including DPCPP as your compiler choice in your Conda build recipes, as shown here. You can also install the compiler packages directly. The DPC++ compiler is an LLVM-based open source compiler capable of compiling for CPU and GPU targets. Data science is so critical to industry that it has grown beyond CPUs and GPUs to XPUs, and Intel's OneAPI offers a promise of heterogeneous compute across XPUs. Data Parallel Python, or DPPY, is a simple unified offload programming model using Python data API standards, Chronos, SYCL, and other extensions and technologies to bring the Python ecosystem to run on different types of hardware, or XPUs. All open standards and all open source. This means that users will be able to run their Python code using popular libraries such as NumPy, SciPy, XGBoost, TensorFlow, and PyTorch on multiple XPUs, taking advantage of the extended compute and memory on both the host and the device. As you can imagine, the technical challenges to this are significant, but the outcomes are very exciting. We are leveraging the popular Numba Python compiler and OneAPI DPC++ compiler technology in order to keep compute on the right devices and to minimize data copy penalties. DPNP, DPCTL, and Numba DPPY packages, all a part of the DPPY XPU package suite, are currently available on the Anaconda Intel channel and are coming soon to the Anaconda Defaults channel. So be on the lookout for more information on DPPY. Finally, here are a series of links for more information on the many tools and technology references in this talk. Have fun expanding your horizons and trying these things out. And with that, I will go to the panel for questions.
Thanks, Todd. This is really exciting stuff. My name is Chris Grundeman. I'm the co-founder of Grundeman Technology Solutions and a co-host of Utilizing AI podcast, but I am not a data scientist nor a programmer. And so I want to kind of kick off here with maybe the dumb question of the day, which is, for folks who are programmers and data scientists and they're looking for these resources, obviously there's a huge toolkit here. We've seen that through a couple slides there. How do I know, when wearing that persona, how do I know when there's an API from Intel or not? Is this something where I just, if I'm using Intel processors, I should just default to always going to look to check for an Intel version first? Or is there a helpline I can reach out to? I mean, obviously these links are helpful, but in that moment when I'm actually in the middle of programming, how do I know to grab the right tool, or how do I know which tool to grab?
Yeah, that's a great question. One of the things that we had as a focus when we started this project is to try to bring our tools to where the users are. So instead of trying to have the users have to come find an Intel site and find that there is a different build of NumPy that's available at this place, and then they have to go hunt it down and find it. We were trying to bring our optimizations to where the users were currently getting their performance packages. So early on, we teamed up with Anaconda, who had the #1 Python stack for data science. And we began working with them to put our optimizations into their mainline packages that they provide. So one of the key places that we include our packages is on the Intel channel on the Anaconda Cloud. Using that channel, it's as simple as including -c Intel in your conda commands for installing packages. So because conda and Anaconda were very popular Python frameworks, you can, very easily using common tools that Anaconda users are familiar with, get those packages from there. As for the kind of how to know what all Intel has, that's one of the reasons why we actually created the AI Analytics Toolkit. It was meant to be a collection of all of our various, various product and components that the data scientists may be interested in using. So that includes our compiler, it includes the performance libraries, MKL, DAL, 1DNN, which is our distributed network. So it includes many tools all pulled into one. It includes TensorFlow, it includes PyTorch, it includes our Intel Neural Compressor, which works in the TensorFlow and PyTorch environments to provide quantization and other optimizations to those frameworks. It includes the Model Zoo, which is pre-trained models and access to those pre-trained models. So we tried to collect all those things into these toolkits. The primary OneAPI toolkits that we have the OneAPI base toolkit. That is essentially compiler, libraries, analyzers, all collected in the base toolkit. We have an HPC toolkit, which adds some additional things to it, such as MPI. And then the AI Analytics toolkit, which adds the Python frameworks, TensorFlow, PyTorch that I've mentioned already. So how do people find those things? To be honest, we have multiple different teams that are working on these various projects, and we're constantly trying to refine our web presence so that people can find the things they need. But we are also trying to bring them to the places where the users are. The Anaconda channel, Conda Forge, which is a big channel for open source development and build of Python packages. We have a presence there now of our packages. And then many of our packages are also available on the Python package index on PyPI. Some of them are not because they're alternate builds of existing projects like NumPy itself. So to get our build of NumPy, you have to come to the Intel channel on the Anaconda Cloud, which you can use via pip and install wheels just like you can from PyPI. But many of our other packages, such as the libraries, are available on PyPI as well.
Yeah, hi, Todd. Thanks for the explanation. My name is Frederick Van Haren, and I'm the founder of Hyphens, a company that provides consulting and services in the HPC and AI markets. Mm-hmm. And I'm also a co-host on the podcast Utilizing AI, and I can be found on Twitter and on LinkedIn as Frederick V. Haren. I am actually a developer, and I think one of the questions I get a lot is, how do I get started, right? I mean, it's already difficult enough that the open source community has a lot of different tools and methodologies available. Is there any particular reason why Intel then decided to deliver compatible or similar products than what available in the open source community, as opposed to unify everything in a single open source package?
Okay, yeah, that's a good question. First of all, our main objective, whenever we have an optimization that we believe we can bring to an open source project, our first goal is to try to get those optimizations upstreamed so that they're available broadly to the entire community. That's the approach we've taken in particular with TensorFlow. So we work very closely with Google to bring our optimizations into mainline TensorFlow so that users don't have this question of, do I get this TensorFlow or that TensorFlow? And what's the difference if I download this binary versus that binary? We really don't want to fragment the user space and for what their users, where they're looking for it. So the TensorFlow builds that we provide in our toolkits are actually builds of the upstream TensorFlow. They do include some of our optimizations, but those optimizations are build options are included in the upstream TensorFlow project. So our first goal is always to upstream first. Now, given the nature of some of the open source projects, that isn't always, possible, or in some cases, it takes a lot of work just socializing the community and bringing them these changes to them so that they can understand what we're doing. And so the timeframes there aren't always fast. So what we try to do is we try to bring our optimizations as quickly as possible to the channels that we control, namely the Intel channel on the Anaconda Cloud. And in the open source, we have github.com/Intel Python. We have a lot of our sources available there. So everything is still open source, and we're trying to keep them available. But sometimes it's faster to bring those benefits to users by getting them published on our own first, or working with partners like Anaconda.
Yeah, and maybe a follow-up question is regarding to architecture. So you talked a little bit about XPU running on different architectures. Do most of the packages you deliver, are they focused on the Intel architecture, or are you focusing as well on what competitors would bring to the market, like GPUs and FPGAs, for example?
Okay, good question. So Data Parallel C++ is our XPU programming model. It's based on an open standard. It uses an LLVM-based compiler, and it's based on SYCL and some other existing technologies. That compiler you can use to program against Intel CPUs, against other CPUs. It can be used for NVIDIA GPUs. Certainly, we're going to make sure it works really well with the upcoming Intel GPUs that are coming on the market. It works right now with Intel integrated graphics on processors. So we can actually run workloads that'll use both the CPU and integrated GPU on some of our workstation desktops that have GPUs integrated on the chip. So you can do all that right now with Data Parallel C++. The compiler itself is actually open source. So you can go right now to GitHub and you can build that compiler and use it there yourself. So it really can run on any of these platforms. Now, certainly our main efforts are focused on making sure that it runs really well in our hardware. But because it's an open standard, really any of our competitors could pick it up, and they could create the driver interfaces for it, and they could use it on other hardware. Actually, some of our early kind of extended goals are going to be to make sure that workloads that can run on GPU will run on NVIDIA hardware and AMD GPUs and our GPUs as well. So there's really no barriers there. Honestly, it was one of the first questions that I had asked when we had been presented with this challenge of programming the GPUs. So how do you do it across, like, where can we bring value to Intel? And where Intel is really committed to betting that that we will be competitive in the hardware market. So our software is meant to work on any hardware. And then it's up to the users to see how much benefit they can get from our actual hardware. And it will be there.
Yeah, I would like to talk a little bit about the slide you showed about the performance improvements with Modin. So one of the reason why this slide is confusing to certain people is in AI we talk a lot about performance, right? And we know internally that you can get performance by obviously getting faster hardware, but you can also get better performance if you're willing to make some compromises at the precision level. So maybe it's good to kind of explain a little bit why, for example, for PyTorch, when you have a 2.8x improvement, that the precision drops from a floating point 32 to an int 8, right? How you can achieve that, and how the loss of precision is not hurting you in the long run. So
were you wanting information on Modin or on PyTorch?
No, I think it's more general, the public, where they say, hey, it's faster, but it's less precise. And so there's a lot of question there. Why do you go and drop precision in order to gain performance? I think it's more of a question where the people don't understand why you would drop precision.
So that's okay. Yeah, sorry. So first of all, there's certainly not the case that you're always dropping precision to gain performance. Okay, so that's definitely not the case, and I hope that wasn't the message that I gave. So there is the ability to increase performance by reducing precision, and that is really up to the decision of the data scientists on the sensitivity of the work that they're doing to the precision that's there. There's quite a bit of work that can be done where going into 32-bit processing doesn't really provide you any more intelligent results than you would if you were to do 16-bit operations, and it really depends on the operation that you're attempting to do. So those we try to leave those decisions up to the developer, and when they want to enable that compression, for example, one of the components of the AI Analytics Toolkit is the Intel Neural Compressor. In the past, they had gone under different names, so it has been the low optimization toolkit, or a low optimization tool, and that's one that uses quantization and some factoring of the size of the registers that are used in order to gain you some performance at the cost of some level of precision. But that tool is enabled or disabled at the discretion of the user. A lot of our other optimizations, for example, what's available in Modin, those actually have nothing to do with the precision of the results. So those most of our performance gains that we get through Python are actually by unlocking concurrency, not by reducing precision. And the unlocking of concurrency, it comes at multiple different levels within the application, right? So for example, I talked early on about some of the NumPy optimizations that we did with MKL package. One of the really beneficial aspects of that is that we were able to accelerate the universal math functions. And a lot of those benefits came from ensuring that memory alignment was correct when we called out to the native MKL functions to unlock some of the vectorization opportunities that are available in MKL and in the processor. So by doing some simple adjustments before we call out to the native code, we can actually unlock a lot of the advantages of the processors now, and without sacrificing any any precision in the operation at all.
Yeah, another thing I see in the market is that people are using the right tools, but they have not recompiled for the latest chipsets. So they might have recompiled their tools a couple of years ago before they were buying new CPUs, and now they are running with outdated or compiled against an outdated architecture. Is there a way to help those customers to kind of help them lower the barrier to recompile? I mean, I think recompiling nowadays is a lot easier than it used to be, but still, I still see a lot of people asking questions saying, hey, how can I make this, how can I fully recompile to take advantage of the latest architectures?
Yeah, sure. So our first answer to that is one of the things that we're really trying to provide people is our binary builds using some of the latest packages. So that's why we have the Intel distribution for Python, is because it is a binary product that can be installed, and it's already compiled using our latest libraries. And that way, users don't have to, in particular on Windows users, don't have to try to be recompiling their software stacks. Instead, we have the Intel distribution for Python, which is included in the AI Analytics Toolkit. It's all compiled with these latest packages. On the other side of that, we do and are trying to keep everything in open source so that these things are available for the users to compile against as they need to. And then the third part of that is now we have even the Intel compiler, the data parallel C++ compiler is available for users to use to build their software. So those are the ways that we're trying to address it. Certainly, if we have customers that have difficulty in compiling their code against our libraries or our products, then we have support forums available for them. They can contact us directly for help. But those are the ways we're trying to address that question, and it is a challenge.
Hey, what's going on, Todd? This is Gerard
Yep.
Cavalinas. I'm the founder of Tech House 570. I also work for Helion Systems as the managed services systems engineer. You could find me on Twitter at @gcavalinas. And to kind of go off what Chris said, I'm no developer. I'm still dabbling myself every day with coding and really getting stronger with automation. And these tools are something astounding I didn't even know existed. I guess my question would be is when you were developing them, and you're going to have novice users of all different ranges, right? From beginners to seasoned individuals. I mean, what were some of the challenges you think, or what really was the key factor in designing this as far as, I'm trying to figure out the best way to word it. Like, what were some of the challenges you had seen when developing this? I know people came to you with certain expectations. What did you find the hardest about, developing this tool set and kind of how it could help everyone?
Yeah, so I think one of the biggest challenges is just the breadth of the Python community, right? There are so many packages that are available. And even when we started the Python project, which is at the kind of the heart of the AI analytics set, there were even already multiple implementations of the Python interpreter that people were using, and they were using it for different reasons, right? To try to, in most cases, it was to try to get around the GIL, the global interpreter lock, to try to get better concurrency and performance. And they were, they had different levels of success with them. One of the things that we really tried to do is, again, we really wanted to bring the optimizations to tools that the Python developers were familiar with and already using. Okay, so instead of a different Python interpreter, we're using and shipping CPython. We're optimizing NumPy. So all you have to do is install NumPy, like everybody installs and uses NumPy, and it operates the same. Same thing with Scikit-learn and Modin. You change your import, it's one line of code, and then you continue to use it with your normal workflows, your normal APIs, even the same code can be used. So we recognize that it's really challenging to pull in, especially these low-level libraries that are extremely well optimized in MKL and DAL. And that's a really hard learning curve for a Python developer. For example, NumPy for years was able to be compiled against MKL's BLAS using MKL's BLAS interface. But we would get constantly questions all the time from people struggling with getting it done well and getting it done right. And so we early on identified that, if we can provide a binary distribution where we solve those problems for people, and all they need to do is pip install or conda install NumPy, and they get the optimizations, that's really the ideal. We don't require people to be doing things out of their comfort zone. It allows them to continue to use the tools that they're familiar with and to really just continue to be productive. And that's what we're trying to attain here.
Hi, Todd. This is Jim Sprinsky. I'm a principal for Zero Defect Computing and also an Oracle ACE director. You can find me on Twitter at Jim the Y Guy. For a little bit of a more abstract question, looking at the speed up that you were able to demonstrate for the Intel extension for Scikit-learn, were there any particular types of operations that were, would you say, more bang for your buck? Perhaps classification versus regression, possibly maybe drawing input or working against, say, a graph database versus a traditional relational data set, anything like that, that would essentially tweak someone to decide, hey, I'll go take a look at this, consider recompiling, as Frederick said?
Yeah, so a couple things. First of all, you actually don't need to recompile anything to use our Scikit-learn, right? You can simply install the Intel Scikit-learn or the Scikit-learn IntelliX extension, and then run the patch command. And then you now are using, under the hood, you're using DAL's implementations, which are outside of the Python objects, so they don't incur the need to gain that global interpreter lock. Okay, so you don't really need to compile anything. You just need to install the extension and enable it. And all of your code that used Scikit-learn before can still import sklearn, and you will get the underlying performance enhancements. So on the question of, are there certain things that give you more benefit than others? The answer is yes. Certain things you'll see more benefits than others. This graph here is actually an example of some of those things. You can see that there is, a 6x performance for elastic net fit, and then a KNN inference is like over 7 times faster. And while you see very small for some of the other benefits, right? So it really depends on the algorithm. The other thing that that factors significantly in the amount of benefit you'll see is the amount of data you're processing. Okay, if you're really processing a very small amount of data, you're not going to see very much of a benefit here. But as soon as you get into the larger amounts of data, that's where your concurrency that you're gaining is really going to be visible. So the bigger your data set, the bigger you're working with, the more benefit you should see. I encourage people who are interested to go look at the Intel extension for Scikit-learn website. There they'll have many more graphs like this that'll show some of the various algorithms that are accelerated. Generally, what we've been trying to do is for every algorithm that we implement in the data analytics library, we are trying to map those to the Scikit-learn interface. So we're trying to cover as much of Scikit-learn's implementation as possible in DAL. Actually, there are more algorithms and there's more benefits that you can gain from one DAL than is available in Scikit-learn even. And so there are some things that you can do. We have another interface library that's called DAL for Pi. And that is provides all of the DAL algorithms. It provides access to them for the Python developer. And that extension for Scikit-learn connects to DAL for Pi connects to DAL. But if you wanted to do like really distributed machine learning using the data analytics library, you can do that directly from DAL for Pi. Scikit-learn is not inherently distributed. It's you run it in a single process, but you can do a distributed mode if you use DAL for Pi. So there's some different things that you can do, and there's a lot of capability there. It does get more technical the deeper you go. The finer or the further down in the stack you run, there are more options and it gets more technical. But there's a lot of information available in the Intel extension for Scikit-learn site and in the data analytics library that can guide people once they're ready to take that step. The part of the beauty of it is it can be as simple as saying, install Intel or Scikit-learn IntelliX patch and run, and you have performance enhancements. But if you really want to get down into the details, you can go all the way down into the data analytics library for the highly technical users and gain even better performance benefits. So it's really accessible across the spectrum. All right, thank you panelists for all your time and questions today. This is a list of links that folks can use to get more information on our tools, on our OneAPI AI Analytics product. There are blogs here from Intel and Anaconda on some of the performance benefits, a lot of information. So use them to try to take your development to the next level, and I thank you for your time.